Consider some objects. Most of the objects we're going to be thinking about have some kind of mass associated with them. So here I have some weights, the weights have some mass. What Newton's first law says is that all objects that have mass have some inertia associated with them. Now what do I mean by inertia? By inertia, I simply mean an object's resistance to changing its motion. So I think it's good to start with an example here. So let's say here's a piece of chalk. The chalk has some mass, but it's not too hard to change the chalk's motion. The chalk's not moving now. There, I can get it to move. It's not that difficult because the chalk doesn't have very much mass. Let's take something with more mass. So let's say I have a bus. Here's a bus. If I want to get the bus to move by pushing on it, say my bus is out of gas, well, if I start pushing on the bus, it is going to take a lot of effort to get the bus to move forward. Why? Well, the bus has more mass than my chalk did. Therefore, it has to have more inertia. It does not want to change its motion. So since it has more mass, it has more inertia, it doesn't want to change its motion. If it starts off not moving, it's going to want to keep being in a state of not moving. So that's why it's difficult to push my bus forward. It has more mass. But it's not just a matter of creating motion versus not creating motion. It's a matter of changing motion. So if instead of my bus being still, let's say my bus was already moving. Boom, there it goes, it's moving. My bus is already moving, and I want to stop its motion. Stopping is another type of changing motion. Inertia simply says that we don't want to change an object's motion. So if I try to stop my bus from moving, I'm going to have a bad day. Because again, the bus has a lot of mass. And just as it's difficult to start an object moving, it's going to be difficult to stop a very massive object from moving as well, because again, more mass means more inertia. And inertia is simply an object's resistance to changing its motion. Now, there's a nice demonstration you can do of Newton's first law. So here, I just have some masses. These are 100-gram masses. I'm just going to stack them up on this sheet of paper. I'll try to get them nice and even. Now, one of the things that we will talk about is something known as a force. So if I want to get an object to move, if I want to force it to change its motion, I have to apply what's known as a force. A force is the physics way of saying just pushing or pulling on something. So for example, if I pull on these masses by pulling on the paper, you can see that I can get the masses to move the paper. Now, what's not trivial is that it actually takes some time for the force to act. So if I pull this sheet of paper slowly, you can see my masses don't go anywhere, they just stay right on the sheet of paper. Or rather, they do go somewhere because they're moving with the sheet of paper, they're actually moving here. However, if I do not give the force enough time to act, so if I don't give the paper enough time to pull on the masses, then the masses should stay where they started. So if I pull this paper really fast, you can see the masses haven't had enough time to accelerate. The force didn't act on the masses long enough to get them to move with the sheet of paper. Now you can see they did a little bit. The bottom mass plate here shifted over to the left just ever so slightly. And the reason is, well, it felt the most direct force because it was directly touching the paper, so it'll move a little bit to the right. But if I did this fast enough, even that mass wouldn't have a chance to move very much. You can see if I do it fast enough, the time it moves a little bit less. So what's going on here, again, is just simple physics. Every mass has some inertia to it. Inertia is the resistance to changing the motion, or you may have heard that an object at rest likes to stay at rest. Well, here, these guys want to stay at rest unless I take some time to push on them with some So Newton comes up with his first law. The first law says objects in motion stay in motion at a constant speed, moving in the same direction. What causes changes in motion? We've called it a force. Well, what do forces actually do? That's going to be the subject of the second law. Now, a natural assumption is to say, well, forces cause motion. Right? It's a natural assumption. Right? Here is a piece of chalk. If I push on it, I can get the chalk to move. Right? So we might make the assumption that force causes motion. This is our assumption. We'll check whether it's true experimentally. We're going to assume force causes motion. Right? Causes an object to move. If force causes motion, then it should be true that if I push with a bigger force, I should get more motion. Or more specifically, I should get more velocity, more speed. If I push harder, something should go faster. Seems to make sense. So we would expect that the force that I apply is proportional to the velocity, or how much motion I'm getting. How fast am I actually moving? So, does force cause motion? We're going to try to answer that experimentally. So, I have here a setup where I have a cart, I have an air track right here. Basically the way this works, it's kind of like an air hockey table. There's little holes in here. Those holes are going to pump air through, and that's going to make this slide back and forth fairly easily. Now, the reason I want to do this on an air hockey table is I want to get rid of any extra forces that I don't want there, things like friction. So if I were to just do this on the table, as this cart were to slide across, you can hear it scraping across the bottom of the table. We don't want that. We want no extra forces, just the forces that I'm going to apply to the cart. So we want to make sure we have this set up like a very controlled experiment. And to create my force, what I'm going to do, I have this string here. I'm just going to hook that string on here. And at the other end of my string, I have a little hangy weight. This is 50 grams. What I am going to do is just hang my hangy weight over the side. There's a pulley here. What I can do, if I get this straight, there we go. What I can do is set this up so that I let my weight go. The weight will pull my cart this way because it's applying a force. The string that is attached to the weight is going to pull on my cart. That pulling is a type of force. Now I can actually change the amount of force that I pull with. All I have to do is put some extra weight on my hangy weight, and now it's going to pull with more force because it's a little bit heavier. So what we're going to do, we're going to measure the amount of force that we're pulling with and see if we can track the motion. Now, it should be true, if force is causing motion, it should be true that the amount of weight that I add, the amount of force that I'm pulling with, rather, will change the velocity of the cart. So, more specifically, we should be able to make a graph. We should have a graph of force versus velocity. So it should be true that if I pull with a certain amount of weight here, a certain amount of force, this should move with a certain velocity. If I put more weight on, I should get a bigger velocity. So I can make a plot of the amount of force that I'm pulling with as a function of the velocity, and I should get something that says that force is proportional to velocity, which would mean that we would get something that looks like a straight line. Let's see if that's what we get. Okay, here's our data. Now, what you can clearly see, here's a plot of our position as a function of time. We can see that our position increases over time. That's to be expected because, after all, we're looking at the motion of the object. But here, our velocity versus time graph, we can see it's a little bit noisy, but the slope is constantly increasing. at no point do I ever reach a constant velocity. Even if I take the smallest weight I have, just take the 50-gram weight, no extra mass on here, and I just hang this over the side. As soon as I let it go, my cart gets pulled, and not only is it getting pulled, not only does it have motion, but it's accelerating. It's constantly accelerating. It never actually reaches a stable, constant velocity. It keeps going faster and faster and faster. So what this means is that it must not be true that force is proportional to velocity. It cannot mean that force causes motion. Force does not cause motion. Does not cause motion. Cannot emphasize that point enough. Force does not cause motion. If it does not cause motion, then what does force cause? So, what do forces do if not cause motion? Forces cause changes in motion. So, forces do not cause motion. Do not cause motion. Forces cause changes in motion. Specifically, changes in velocity. So it doesn't cause, forces do not cause an object to move. You can be moving, you can have velocity without any forces. In fact, if you have no forces and you have velocity, you will keep moving forever and ever and ever. Nothing will stop you. Objects in motion will stay in motion unless acted on by an outside force. If I do have a force, specifically I should say, I want a net force here. Describe what I mean by that in just a sec. If I have a net force, then I can get not just motion, but some sort of change in motion. What is a change in motion? Well, that means my object has to be accelerating. Could be speeding up, could be slowing down, could be changing directions, but it has to be accelerating in some form or fashion. So we showed that the force, and I'm going to write this in my vector symbol here because direction does matter for forces. I can be pushed or pulled in a bunch of different directions. My force is not proportional to velocity. It's proportional to the acceleration. And again, I want my net force. By net, I just mean the total force. So in my experiment, I just had a string pulling on a cart. I could have a bunch of strings pulling on a cart or pushing on a cart. I could have a bunch of different forces. Maybe I'd put in some springs or some other weird gears that cause my cart to be pushed and pulled in different directions. But when I add up all of the forces, I take the net force. Net just means add them all up. I add up all the forces. That gives me something proportional to acceleration. One thing I should note, this funny symbol that looks like an E, like a funny shaped E, this is the Greek letter sigma. This stands for sum. As in sum up all the forces, add them all up. If you add up all the forces, you get something that is proportional to the acceleration. In fact, we're going to do one better than this. We're going to say that if we add up, I'll do it down here. If we add up all of the forces, what you will get is exactly equal to the mass of the object times the acceleration. Botch this equation off because it's important. Let's work out the units. Let's just go over once more to define what each of these things are. This is my net or total force. We'll work out the units for force in just a second. This is my acceleration. we know that acceleration is measured in units of meters per second squared. Meters per second per second. That's my mass. My mass, as we know, is measured in kilograms. Therefore, just taking mass in kilograms times acceleration in meters per second squared, I know that force has to have units of kilograms meters per second squared. Now, kilograms meters per second squared is kind of a mouthful. So we try to come up with a shorthand for that. We give it a little nickname. We call this a Newton. So the unit of force is kilograms meters per second squared, or equivalently 1 Newton. 1 Newton is the same as a kilogram meter per second squared. Okay, let's see if we understand Newton's second law. Again, we add up all of the forces on an object. That tells me its mass times its acceleration. Again, direction here matters. The net force has got to be in the same direction as the acceleration. Again, we'll put this in a box because it's important. Important equations always get boxed. Say I have a 2 kilogram ball here and a 1 kilogram ball here. Which one is going to, well, let's say they have the same force on them. So they both get a force of 1 Newton. Which one will accelerate faster? Let's say they've got the same force. That doesn't matter. The 2 kilogram ball has a bigger mass. Therefore, to maintain the same force, it's got to have a smaller acceleration. To put that another way, if you're heavier, if you're more massive, and I push on you, you're not going to accelerate as much for the same amount of force. Right? I have to push with more force to accelerate heavy objects. Let's try that again. One more time. Let's say I have 2 objects, now they have the same mass. Let's say 1 kilogram, and again 1 kilogram. Now, I give this guy a 2 Newton force, I give this guy a 1 Newton force. Now notice what I did there. The 2 Newton force has a longer arrow than the 1 Newton force. When we draw force vectors on an object, we try to make the vectors about the same size, at least relatively the same size as the actual forces. So this arrow should be twice as big as that arrow. 2 Newton force versus a 1 Newton force, which one's going to accelerate more? Well, the 2 Newton force, that's bigger. However, they have the same mass, which means therefore the 2 Newton force is going to accelerate more. Makes sense. If I push harder on an object, it's got to accelerate more than if I push not as hard. Let's do an example of a force problem. Now there are certain steps that you're always going to want to follow when doing force problems. Step number 1, draw a picture. Cannot emphasize this enough. Draw a picture and preferably make it a big picture. So here we go. Don't be afraid to take up half of a page with us. Big picture. Say I have a block. The block has some mass, m. Let's say that mass is 2 kilograms. So I'll say over here, m is 2 kilograms. Let's have 2 significant figures. Mass is 2 kilograms. Step number 2. We want to identify what our forces are and put them in what's called a free-body diagram. Free-body diagram. What that means is I am going to draw my forces directly on my picture. So let's say I have a couple of forces here. I'm going to draw both forces. Say I have a force over here. That's this big. I'll call this force 1. A couple of points about drawing the force arrows. I start the arrow where the force is being applied. So let's say I'm pulling on the block with a string that's tied right here. I start my arrow right here. Second thing about the force arrow is the length has got to be proportional to the strength of the force. It's just like any vector. If the vector is this long, that length should be proportional to how big the force is. Let's say force 1, let's say it's a 6 Newton force. That means that this length is going to be, we'll call that 6 newtons. Now, suppose I have a 4 Newton force pulling in the other direction. I've got a 4 Newton force over here. I'll call that force 2. Okay, there's 2 strings. One string's pulling this way, one string's pulling that way. Force 2, we said, is a 4 Newton force. Well, that should be a smaller arrow than this arrow because it's a 4 Newton force. In fact, 4 is 2/3 of 6, so this arrow should be about 2/3 the size of this arrow. Might need to make it a little bit longer. Now you don't need to be super precise with this, but you want to get a rough sense for how big each of these are, because then you can visually look and say, well, this arrow is bigger than that arrow. Therefore, the block should be accelerating to the right. It just helps you out, helps you visualize what the forces are doing. So that's step number 2. This is what's known as a free body diagram. I will often abbreviate that as just FBD for free body diagram. If I ask you for a free body diagram, that means I want you to draw the arrows, the force arrows on the object. Now, a couple of other notes about free body diagrams. Don't draw any other vectors on here. A lot of times people like to put the acceleration or the velocity. Don't worry about that, that's just going to confuse matters. We only want the forces on this diagram. The reason we only want the forces on that diagram are because now we're going to add those forces up. Because we're getting to step 3, which is we want to sum up the forces in the diagram. Here we go. Step 3 is we want to sum all the forces. Now, for the time being, we're sticking to problems in 1 dimension. Later on, we'll do force problems in 2 and 3 dimensions. Those are going to be a little bit harder. But for now, we're just going to sum up the forces moving left and right. I have 2 forces. I've got my 6 Newton force and I've got my 4 Newton force. So I'm going to say that's going to be force 1. And then I have to add up force 2. Now I have to be careful about how I do that. So we said that this is force 1, but I have not defined any direction. Specifically, I need to know what's the positive direction. So to do that, I'm going to say that this direction is the plus direction. So to the right, we're going to call anything pulling to the right a positive force. Anything pulling to the left is going to be a negative force. Again, it's a vector, so I need to take that into account. So force 1's pulling to the right, that's the positive direction. So that'll be plus force 1. But force 2 is pulling to the left, that's in the negative direction. So I will say this is going to be minus force 2. And I've added up all my forces. Now, I've done 2 forces here. I could have 3 forces, I could have a million forces. I could have any number of forces on my block. I want to sum all of them up because we know by Newton's second law that when I add up all of these forces, we have to get the mass times the acceleration. Since we're working in 1 dimension, I'm actually going to drop these vector signs, so we don't really need them. We'll need them when we get to 2 and 3 dimensions. But for now, let's just drop it to make our life easy. Now, I haven't actually asked for a question yet. I haven't said, well, what are we solving for? Are we solving for acceleration or the mass? I haven't given you the acceleration yet, though, so let's solve for that. So generally the way these problems will work is you'll do these steps. You'll draw a picture, you'll make your free body diagram, you'll sum up your forces. That's step 3, sum the forces. And at this point we have an algebraic equation. Now, I could have left any of these variables out. I could have said solve, in this case we'll solve for the acceleration. But I could have left out force 1. Maybe I gave you the acceleration, but I didn't give you force 1. And you're going to have to solve for what the missing variable is. So here, let's just check to make sure we have enough information. I gave you force 1, so I know what that is. Gave you force 2, you know what that is. I gave you the mass. The only thing that's missing is the acceleration, so I want to solve for the acceleration. Now, it didn't have to be that way. I could have left out force 1 and given you the acceleration and said, hey, what's force 1 that gives you this acceleration? Or I could have left out force 2, or I could have left out the mass. Any one of those variables I could have left out. Because as long as only one is missing, we can solve this equation using algebra. So let's do that. Let's solve for what our acceleration is. Let's see, I have a mass over here. I want to get acceleration by itself. Let's divide both sides of the equation by the mass. Mass cancels out on this side, stays over there on that side, and we're left with the acceleration is equal to force 1 minus force 2 divided by the mass. Carrying that over to this side, what we can see, if I plug numbers in, that would mean force 1, we said was 6 newtons, 6.0 newtons, minus force 2, so it'll be minus force 2 is 4 newtons, divided by the mass, which was 2 kilograms, 2.0 kilograms. You do want to pay attention to significant figures. I know I've got 2 significant figures in each of my numbers, therefore I need 2 significant figures in my answer. 6 minus 4 is 2, divided by 2 is 1. We should get 1.0 meters per second squared for my answer. Now that's the process. Remember, there's a few steps that we've got to do. Step 1, draw a picture. Step 2, make your free body diagram. Draw the forces in, follow your rules for making a free body diagram. Step 3, sum up the forces. Step 4, solve the algebra for any variable that's missing that we want you to solve for. 4 steps. If you follow these steps, doing force problems should be pretty straightforward. Now that we've gone over free body diagrams, I have a riddle for you. So I have a wire spool here. It's got 2 outside rims and an inside cylinder. To the cylinder I have attached a cord. It's basically just a piece of string. And your riddle is what's going to happen when I pull the cord. So the first time I'm going to do this should be pretty straightforward. Here's my spool. I've got the outside rim, the inside cord, or the inside cylinder. The cord is wrapped around that and it comes over like this. What's going to happen when I pull the cord this way, to your left, to my right? Well, in that case, it should be pretty straightforward. Pull the cord to the right, the spool moves to the right, moves to your left. So it moves this way. All that's happening is the spool starts to rotate, and it starts to roll along the floor, and it moves over to the left. Now I'm going to do the same thing. Well, what's going to happen this time if instead of bringing the wire over the top, I bring it from underneath? So in this case, here's my floor, here's my spool. Now I'm wrapping the wire around the other way. The wire is going around clockwise now. It comes out the bottom of the spool. So what's going to happen this time when, let me just wrap this up one more time. What's going to happen when I pull the wire when it's wrapped around the bottom of the spool? So your options are, these are really the only options, is it going to move to your left? Is it going to move to your right? Or is it going to stay in one spot? I'll give you a few minutes to think about that, and then we'll come back with the answer. Alright, let's see what happens. I'm now pulling the string of my spool here from the bottom. And if I'm pulling from the bottom, you would expect that it will start to rotate the other way now. And certainly that's true if I just kind of balance it in my hand. Certainly that's true. It starts to spin the other way. But let's see what happens if I actually try to pull it. I'm going to give myself a little more cord here. Let's see what happens if I try to pull it to the left. And see, it goes to the left. Again. Goes to the left. Now you might be asking yourself, well, what happens if you try pulling it really slow? I go slow, still goes to the left. Well, what if you pull it really fast? Well, fast is a little bit less stable. Let's see what happens if I try to pull it really fast. Still goes to the left. In fact, it doesn't even matter how fast I pull it. It's always going to move to the left. Why does it move to the left? When I pull the spool, it wants to turn the other way. If it's rolling clockwise for you, that would mean it wants to roll to the right. Why does it end up going to the left? It goes back to our free body diagram. What forces are on this spool? Well, there's only one force. The one force is pulling it to the left. Therefore, if I look at Newton's second law says if I add up all the forces, I have to get the mass times the acceleration. Force equals mass times acceleration. Mass is always positive. The force, whatever direction I'm pushing in, I have to accelerate in that direction. If I've got a net force pushing to the left, I've got to move to the left. Doesn't matter if the spool wants to spin the other way. Still got to move to the left.